There are two velocities. One, he talks of thermal velocity. Now, this is the thermal velocity. That means like something is at some temperature, piece of wire is at some temperature, room temperature, is lying in the room. The electrons will have some motion. This is the free electrons and they are moving around. But then he says their average velocity will be zero. They won't be moving. The average of all of them will be zero. Okay. So if there is a wire and you got the all these electrons moving around, the average of them, they won't be moving in front or back. So that means effectively no current is being conducted. Okay. At that moment, if you apply a field, if you apply a battery with the, what is a battery? What is a battery? You are applying, there's a wire and you have some electrodes. You have some electrodes and you apply put the wire in between. And what happens is there's a positive charge here and a negative charge here. So the negative ions are inside very close to the electrode. They start pushing this. Okay. So, so what happens is this starts moving. This starts moving. So if some electron which would have started at A would have ended at B, it actually ends at B dash, because this motion here is because of the electric field. Now, the electric field is always from the positive towards the negative. That's why this arrow is there. And the electrons will always move towards the positive side. They are moving towards this side. Now, this, he says, is caused by the force. Now, if something is moving, there has to be a force. The force is QE. You see, F, force per unit charge, is electric field. So force is QE. And the acceleration is a force by mass. So that's QE by M. That's why this, he gives us the acceleration. Now we employ the equation V is equal to U plus AT. Now for this is for each electron. This is for each electron, not for the average. The average would be zero. This is for each electron, and this is the initial velocity, thermal velocity, and this is the velocity with which is moving under the electric field, and this is the acceleration to the electric field, and this after some time you would find it somewhere else. This, he says, actually gives very strange results. If you average out the whole damn thing, it that will give you the drift velocity, and that drift velocity, because the average thermal is zero, so this becomes zero, comes out to be this. And then there's another strange thing. This, you would expect a velocity with an accelerated motion to go on increasing. He says no, it doesn't go on increasing. It kind of, this is a constant, the time. Why is the time constant? It's called it's a it's a it undergoes collisions, and it's like if you drop a ball from a staircase, the ball speed, it goes on increasing, then hits, then slows down, then hits, then slows down, then hits. So it moves at a constant velocity, and that's called the drift velocity. And this collision with the ball with the staircase is the same thing as the electrons hitting the atoms or the ions in the lattice. So they keep on hitting, like the ball hits the staircase each time it falls. So it doesn't really accelerate. I mean, the velocity remains constant because it keeps on getting a collision, a hit. And so this is the drift velocity, is a constant velocity, even though there is a force. So one thing is clear, this is not like normal motion. Even if there is acceleration, this will become constant because this is constant. This is constant. This is constant. This is constant. In normal motion, V is equal to U plus AT. Even if this is zero, acceleration is constant, time will elapse and the speed will increase. But here it doesn't. Then we come to another important point. He says, if a charge is moving, and he talks of the number of free electrons in per unit volume. So he takes some section D with some area, and he says volume is A into D. Then he says the number of electrons per unit volume, which depends whether it's aluminum or copper, more in copper compared to aluminum or other non-metallic things. So this into AD is the total number of electrons, and that you multiply by charge, that's the total this thing. Now, out of all these terms, current is Q by T. Who's changing? The number of charge is not changing per unit volume, that's fixed. Area is, he's taken some value. D, he's taken some value. All these are fixed. E is the charge, that is also fixed. So this he says, if you divide by T, you are basically, you are trying, this D by T is that speed with which it is moving. And if that is nothing but, that's nothing but the drift velocity, and this is not changing because even of under accelerated. So the formula becomes, instead of this n a d e by t, it becomes n a, this is drift velocity e, that's, and he says this is true for, this is true for all gases, or even if like in semiconductor there are holes, but in that case you will have q instead of. So this is true everywhere because it's quite obvious, it's just the speed. So whatever the speed of the mobile carrier, the area is and this, so all these this formula then converts to V is equal to IR, and then you can actually find the resistivity in terms of all this. I'll show you. I'll just show you. Hold on. You understood this? This formula says the drift velocity is dependent on the charge, the electric field, the mass of the electron, and the relaxation time, the time between two collisions. This is constant. Now, if you see this is the same thing I've written. And we also know that I is equal to NeAVD. So here you have this, you can substitute instead of the drift velocity. This is the relationship between drift velocity and current. This is the relation between drift velocity and the electric field. The electric field is nothing but, you will come to know, is potential difference over per unit length. This is potential difference per unit length. So you can write this as E, instead of E, you can write V by L, and you just now got an expression which relates the current to the potential difference. And this is nothing but V is equal to IR, the Ohm's law. He is trying to get V to the other side. I he gets here, and he gets this term. This is nothing but the resistance, because V by I is nothing but the resistance. So this is nothing but the resistance. And we also know that the resistance is rho LA. You've got these terms L by A here, and this is the resistivity. So the resistivity is nothing but N, M n by e square tau. So these, the number of the resistivity. This is the resistance. This whole thing is the resistance. This whole thing is the resistance. And so what have we just now found? You know, when you were taught in GCSE, R is equal to rho LA. This rho is nothing but the number of electrons per unit and the relaxation time are specific to a particular metal, whether it's, how is its lattice, how many free electrons are there, that is dependent. And the n, this is the number, the collisions, you know, the lattice. So this is how maths comes into physics. So this, all these are related.